Hello my friends and welcome back to the Today Machine channel. In this video we will explore the whole process from recycling scrap steel to manufacturing giant bearings. The billet manufacturing process at Shahroud Steel, Iran, begins with the melting of steel scrap in a 12 megawatts, 25-ton induction furnace. Induction furnaces are widely favored for their energy efficiency and ability to minimize heat loss during the melting process. Electrotherm steel frame induction furnaces are well suited for this operation, with capacities ranging from 500 kilograms to 60 tons. These furnaces are built with heavy structural steel for durability and are equipped with thick-walled rectangular coil sections to reduce coil losses and enhance energy savings. Additionally, features such as a fume extraction ring and insulated furnace lid ensure that heat loss and air pollution are minimized. Once the steel scrap is melted, the molten metal is transferred to the high-speed billet caster. This modular and compact billet casting technology is ideal as it allows for quick installation and minimal disruption to existing infrastructure. The caster's design ensures operational flexibility, allowing for easy size changes and the potential for future expansion by adding more modules. The PLC-based secondary spray cooling system optimizes cooling and minimizes scale formation, which is crucial for maintaining the quality of the billets. Additionally, the motorized tundish trolley and forced mold lubrication system contribute to the efficiency and reliability of the casting process. Given the environmental concerns associated with steel manufacturing, Shahroud Steel has implemented a comprehensive air pollution control system, APCS. Industrial pollution, particularly from steel plants, is a significant contributor to air pollution, making the installation of effective APCS crucial. Electrotherm's clean air solutions are designed to meet stringent government norms, such as the requirement for emissions to be below 50 milligrams per Newton meter cubed in certain states of India. The APCS includes fume extraction systems that capture and filter hazardous particulate matter and toxic substances released during the melting and casting processes, ensuring compliance with environmental regulations. Supporting these critical systems are the electrical and cooling systems, which are designed to handle the high energy demands of the induction furnace and billet caster. Efficient material handling equipment ensures the smooth transportation of molten metal and billets throughout the manufacturing process. These billets are rectangular or square cross-sections and serve as the starting point for the production of steel rods and rebars. The manufacturing process starts with the billets being fed into a billet reheating furnace. This furnace heats the billets to the required rolling temperature, typically around 1100 to 1200 degrees Celsius. Proper heating ensures the billets achieve the necessary plasticity for the subsequent rolling process. Once heated, the billets are passed through a series of rebar rolling mills. These mills consist of multiple rolling stands that progressively reduce the cross-section of the billets while simultaneously elongating them into rods or rebars. The rolling process imparts strength to the steel through mechanical deformation, and it often includes the formation of ribs on the rebar surface, which enhances the bond between the rebar and concrete. After rolling, the hot rebars undergo rebar cooling on a cooling bed. This controlled cooling process, known as thermomechanical treatment, involves quenching the hot rebars with water to create a hard surface layer while retaining a softer, more ductile core. This process improves the rebar's mechanical properties, such as strength and ductility. Finally, the cooled rebars are subjected to cutting and bundling. They are cut into standard lengths using shearing machines and bundled together for ease of handling, storage, and transportation. Hot rolled bar manufacturing at Scott Forge Bar Mill in Clinton, Wisconsin, is a specialized process that combines forging and rolling to produce high-quality bars. Starting with a preliminary forging process, the center of the bars is consolidated to ensure internal soundness. The bars are then subjected to planishing, where they are run through a set of rollers multiple times, giving them the smooth, rolled surface customers expect. Scott Forge offers bars ranging from 6 inches to 16 inches in diameter and up to 40 feet in length, with larger bars made on open die presses. The Tartan Bar Mill is particularly well suited for large orders or spot buys over 80,000 pounds. The well-equipped bar mill has dedicated planishing, cutting, heat treating, straightening, machining and testing equipment to ensure consistent high quality and fast turnaround times. The development of modern manufacturing technology has significantly impacted the production of grinding media grinding balls, enhancing their quality, efficiency, and durability. Automation and advanced materials have been key drivers in this evolution. For instance, the use of automated molding machines in foundries has increased production rates by up to 30%, reducing labor costs and ensuring consistent ball size and weight. Heat treatment processes, crucial for achieving the desired hardness, have also seen improvements. Induction heating technology now allows for precise temperature control, leading to a more uniform hardness distribution, which can increase the lifespan of grinding balls by up to 25%. Advanced alloy compositions have further enhanced the wear resistance and impact toughness of grinding balls. High chromium cast iron balls, for example, now dominate the market due to their superior performance in wear-intensive environments. These balls can last 2 to 3 times longer than traditional low chromium or forged steel balls, reducing operational costs in industries like mining by as much as 20%. Additionally, the adoption of quality control technologies, such as X-ray fluorescence, XRF, and automated defect detection, ensures that each ball meets strict specifications, further boosting the reliability and performance of grinding media in various industrial applications. The Anyam Skew rolling machine, operating in Turkey, is part of an automatic production line for manufacturing grinding balls. The process begins with a feeder system that loads raw steel bars into the furnace, where they are heated to a suitable temperature for forming. Once the steel is sufficiently heated, it is transferred to the skew rolling miller. In the miller, the steel is subjected to a high-pressure rolling process between two specially designed rollers. This forms the heated steel into spherical grinding balls. The machine mentioned is a 40mm model, capable of producing 30mm, 35mm, and 40mm balls at a rate of approximately 80 balls per minute. The rolling process ensures that the balls are formed with precise dimensions and a consistent surface finish. After forming, the balls undergo a quenching process, where they are rapidly cooled to achieve the required hardness and strength. The machine can produce balls ranging from 20mm to 100mm in diameter, making it versatile for various applications. This efficient production line is crucial for meeting the high demand for grinding media in industries like mining and cement production. The manufacturing process of chrome steel balls begins with the selection of raw materials, which are steel balls. This is followed by a critical heat treatment stage, where the balls undergo a series of carefully controlled steps to enhance their hardness and durability. The heat treatment process, automated for consistency and accuracy, involves 6 key stages: storage feeding, heating in a furnace, quenching in a tank, cleaning, recooling, and tempering. Post-heat treatment, the balls are subjected to hard grinding, which refines their dimensional accuracy, followed by lapping to achieve a smooth and polished surface finish. Quality control is paramount throughout the manufacturing process. The company employs 6 photoelectric appearance testing machines to ensure the surface quality of the balls. In addition, the world's most advanced bearing ball quality control equipment, the AVKIO eddy current test machine, is used to detect surface and subsurface defects, guaranteeing that only defect-free balls proceed to the next stage. Once the balls have passed quality inspections, they undergo a thorough cleaning process before being packaged. An American automatic packaging machine ensures precise counting and packaging, tailored to meet the specific requirements of customers. With an annual production capacity of 4,800 tons, and 90% of its products exported to more than 10 countries, the company plays a significant role in supplying chrome steel balls for applications such as wind turbine slewing ring bearings, construction machinery, and oilfield equipment. The inner and outer rings are forged from high-quality steel, creating a strong, uniform structure. After forging, the rings undergo precision machining, which includes turning, grinding, and honing. These steps are essential to achieve the exact dimensions, smooth surface finish, and tight tolerances required for the rings to fit seamlessly within the bearing assembly. This meticulous process ensures that the bearing operates smoothly, reduces friction, and can withstand high loads and rotational speeds over extended periods. SKF spherical roller bearings are manufactured with precision and quality, even today, at the SKF Luton facility, which produces approximately 3 million spherical roller bearings annually. The manufacturing process begins with the arrival of heat-treated component pieces, including the inner and outer rings, sourced from suppliers around the world. The first step in production is grinding the faces of both the inner and outer rings to ensure they are flat and parallel. The outer diameter of the outer ring, the sphere, and the inner bore of the inner ring are then ground to achieve a smooth finish. Following this, the inner ring raceway is ground and honed to meet specific surface characteristics, which are critical for the bearing's performance. After grinding, the rings undergo a meticulous washing and drying process to remove any dust, debris, or contaminants. The rollers, guide rings, and cages are then assembled with the rings to form complete bearings. For sealed SRBs, once assembled, grease is added, and the seals are fitted. The bearing designation is laser etched onto the surface for identification, and each bearing undergoes a thorough inspection to ensure it meets stringent quality standards. To prevent corrosion, the bearings are preserved with a protective coating. Finally, the bearings are carefully packed and prepared for shipment to customers worldwide, ensuring they arrive in optimal condition, ready for use in various industrial applications. The manufacturing process of bearings at Zen's factory begins with cutting steel rods, handling bars up to 200 millimeters in diameter. Each day, over 800 meters of stainless steel undergo precise lathe machining, creating more than 14,000 grooves. Following this, raceway grinding is conducted to achieve the exact shape and depth necessary for optimal bearing performance. The bearings are then subjected to quenching, with temperatures reaching up to 1050 degrees Celsius for stainless steel and 900 degrees for chrome steel, ensuring the material's hardness and durability. After heat treatment, the raceways are finely polished to achieve a smooth finish, critical for reducing friction during operation. Before assembly, Every bearing undergoes tolerance testing to ensure it meets the stringent requirements. With a production capacity of 3 million bearings each month, each unit is laser marked according to customer specifications. The final inspection and testing take place in a German-managed quality control center, ensuring adherence to the highest standards. Once the bearings pass inspection, they are sealed, boxed, and prepared for shipment, reaching customers in over 30 countries worldwide. Automatic bearing assembly process begins with feeding the rings, where the outer and inner rings are automatically fed into the assembly line. Next, the measuring of the outer and inner rings is conducted to verify that they meet the required specifications. This step is crucial for ensuring the correct fit and functionality of the bearings. Following the measurements, the selection of balls occurs. The balls must be of uniform size and quality to ensure smooth operation and longevity of the bearing. Once the balls are selected, the joining of the rings takes place, aligning the inner and outer rings in preparation for ball insertion. The fitting of the balls involves placing the balls between the rings, followed by the spacing of the balls to ensure even distribution around the bearing's circumference. This step is essential for reducing friction and wear during operation. After the balls are properly spaced, the fitting of the cage is performed. The cage holds the balls in place and ensures they remain evenly spaced. Finally, the process concludes with cage riveting, where the cage is securely fastened to maintain the integrity of the assembly. Manufacturing large-size roller bearings, especially with dimensions like those of a spherical roller bearing, weighing 4,420 kilograms, presents numerous challenges. The scale of these bearings demands advanced engineering and precise control throughout each stage of production. Forging is the first critical step, requiring large billets of high-quality steel. Achieving uniformity in the material during forging is challenging due to the sheer size, which can lead to internal stresses and defects. Turning the forged rings and rollers necessitates the use of massive, specialized lathes capable of handling the significant weight and ensuring exact tolerances. The turning process must be precise to avoid issues later in assembly. Cage drilling is another complex step, where the precision drilling of holes for the roller elements must account for the bearing's size and the thermal expansion during operation. Heat treatment is crucial for both rollers and rings, ensuring the right balance of hardness and toughness. However, uniform heat treatment is difficult at this scale, as temperature gradients within the large components can lead to inconsistent properties. Grinding these large components to the final dimensions is a precision task, requiring meticulous attention to detail to achieve the required surface finishes and dimensional accuracy. Quality control is especially challenging due to the need for detailed inspections of such large components, where even minor defects can lead to significant performance issues. Assembly involves handling and fitting heavy components with precision, and packing must ensure protection against damage during transport. Finally, mounting these bearings on site requires specialized equipment and expertise to avoid misalignment, which could compromise the bearing's performance. These challenges make the manufacturing of large-size roller bearings a complex and demanding process, requiring state-of-the-art technology and skilled personnel at every stage. Raw material selection. The production process begins with the selection of raw materials. The primary materials used are round bars and square bars, typically made from carbon steel, stainless steel, or alloy steel, depending on the specific requirements. The raw materials are inspected for quality before they are cut into smaller pieces, the first step in shaping the flange. Cutting and heating. Once the raw materials are cut to the required size, the next step involves heating. The cut pieces are heated to a very high temperature to make them malleable. Forging and shaping. After heating, the material is moved to the forging section. Here, the heated metal is placed under immense pressure to shape it into the desired flange design. Forging is done using heavy-duty machinery that can exert significant force, ensuring the metal takes on the correct shape. The inner diameter of the flange is formed during this stage, and the outer shape is also refined. The high temperature ensures that the metal remains pliable, making it easier to achieve the precise dimensions required. Surface treatment. Following the forging process, the flanges undergo surface treatment. This step is crucial for enhancing the durability and appearance of the flanges. The surface is smoothed using specialized machinery, which is controlled by computers to ensure precision. The aim is to achieve a smooth and even surface, free of any imperfections that could affect the flange's performance. Surface treatment also involves drilling holes for bolts, which are necessary for connecting the flange to other components in the piping system. Coating and finishing. The next step in the process is coating. The flanges are dipped into a container of protective coating, which can vary depending on the intended use of the flange. For instance, flanges intended for outdoor use may be coated with a weather-resistant layer. The coating not only provides protection against corrosion but also enhances the visual appeal of the flanges. The coating process is done carefully to ensure every part of the flange is evenly coated. Once coated, the flanges are dried in an oven set at a high temperature. The drying process is crucial as it ensures that the coating adheres properly to the flange and hardens to form a protective layer. The flanges remain in the oven for a specified period, usually around half an hour, until they are completely dry. Final inspection and packaging. After drying, the flanges undergo a final inspection to ensure they meet all quality standards. Any flanges that do not meet the specifications are rejected and sent back for rework. The approved flanges are then packed carefully to protect them during transportation. Each flange is wrapped in protective film and placed in a container, ready for shipment.